Thank you all for coming along. I always hate it when I get the graveyard shift. Who did go to the party last night? You guys have done fantastically well. So welcome to Storage in the Windows Azure platform. My name's Chris Auld. I do not work for Microsoft. I work for we think we're big, but we're actually pretty small, Microsoft Gold partner down in the sunny South Pacific island nation of New Zealand. I am neither a hobbit, nor am I New Zealand's fifth most wonderful folk music comedy duo. Everyone, Flight of the Conchords fans? Yeah. Contact details here. Happy to receive your emails. Follow me on Twitter. I will chuck some content up on my blog, which is on the last slide. That way you have to stay till the end to find out where to get the bits. We're going to move pretty quickly today. I got lots and lots of content. This is really a sort of a mashup of about 2 or 3 sessions that I do as part of my deep dive Azure Architecture Workshop Day. This is all about giving you guys some of the learnings that we've taken from being early adopters of this stuff. This is not hello world crap, right? We're going to touch quickly on what some of the Azure storage stuff is, but then we're going to basically go, how the hell do you use this stuff? And they're really architectural concepts. The dev stuff's easy, right? I can get any old monkey to write the code, but it's actually those upfront decisions that you make that will manifestly affect the way your application runs, and in particular, how much your application costs to run. So we're going to talk about the various Azure platform storage types, both Windows Azure Storage, SQL Azure. We're going to talk about strategies for optimizing storage, partitioning, right, for both data volume and performance. We're going to talk about NoSQL data modeling. We're going to talk a bit about the CDN distribution model. And we're going to talk about how we optimize our application for cost. On the way through, we're going to talk a bit about this application that we built called Ticket Direct. Ticket Direct is our canonical cloud application. And the reason they're the canonical cloud application is they have spiky workloads. All right? Most of the time running along, 2 or 3 servers. 9 o'clock one morning, you need 20, 30, 40, 50, 60 servers. Very hard problem to solve. Impossible problem to solve unless you have cloud computing, because you cannot justify the capital cost of all of that gear sitting around doing nothing for most of the year. And so we built Ticket Direct out, and we're working with them to build out a new platform. We do some interesting things around storage. For example, we do use SQL Azure. They have existing legacy SQL Azure stored procedures that they need to use to enforce the golden rule of ticketing, which is, ladies and gentlemen? Say again? Availability? 1 bum per seat. Absolutely. Availability, 1 bum per seat, right? Very, very important, which means we kind of want a proper relational database that understands concepts like concurrency and locks and all of those things that we kind of take for granted. So we do that, and in order to achieve performance, we actually take a particular event, and the morning of the game going on sale, we chop that event up into 50 databases. We run 50 databases for a day to sell our event, and then we consolidate it back down again. Right? So cheap, ladies and gentlemen, is Azure, SQL Azure pricing, that we reckon we could chop it up into 1 database per seat in the stadium and still make a good margin. Right? So there are these amazing new possibilities for us to be able to achieve the sorts of performance, right, that you could never do before. Because most of our competitors, all they're going to do is they're just going to fall over flat on their face when that big game goes on sale. We use Azure Table Storage to store information about our partitions, or information about which portions of the venue still have seats available. High performance, read-only. We use queues, worker roles, and a bunch of other things to actually manage the grooming of this data. So what we're talking about today is trying to give you guys some insight into some of the learnings that we took away from building this application. We will, however, start with the Azure Platform Storage fundamentals. And the reason for this is that we will have people who haven't seen it before. So let's start by talking about Azure Storage. Azure Storage comes in 4 different variants, right? Up from 3 last month. Those are blobs, drives, tables, and queues. They all share a set of common properties. They are all very much designed for the cloud. They are based on the idea that we have 3 replicas of your data spread out throughout the data center. That data is spread across what we call fault domains. Right? That means we don't stick all 3 copies of your data on 3 machines in one rack. Because if that rack catches on fire, your data's toast. Right? And the backup of your data relies on the fact that that data is spread throughout the data center. We do have guaranteed consistency. When you write something into Azure Storage and you get a return back from the RESTful web service, that data is committed. You go and do another write, you're going to get that data back. That is not always a property offered by some of these high-scale cloud storage systems. You can access Azure Storage via a set of RESTful web service interfaces directly from the internet. There's also within the Azure SDK a set of APIs that you can use to access that storage as well. One of the nice things about it being a RESTful service interface is that we can do a GET at a particular URI. What that means is if we stick an image file up into Windows Azure Blob Storage, we can do a GET at that URI and have that image returned. This therefore means that we can point clients directly at Azure Storage. Indeed, Azure Storage can, for static web content, become a platform that you use to serve up content in its own right. I.e., you can use storage alone to host something like your blog site, if you're not generating your content dynamically. Very, very cheap if you do that, right? Like cents a month. It does not require compute, right? So we don't have to have compute. We can stick stuff up in blob storage. We can have on-premise apps using blob storage. And you basically get a unique URL for each of your storage types that you'll be using, and they become part of your blob storage account that you create through the Azure portal. To drill down a bit, so blobs are your primary mechanism for storing binary data in Azure Storage. They're scoped by a container, so you basically create containers and then you create uniquely named blobs within those containers. Your container ends up providing you with an addressable URI, again, that you can do a GET at and receive that data back, provided your container is public. We have 2 different types of blobs now. We have what are called block blobs and page blobs. Right, block blobs are really designed for situations where you need to stream the whole file back. Page blobs are designed for situations where you need random access to that blob. Each blob has a set of metadata, basically name value pairs up to 8K worth of data that you can access independently of the blob. So drives are something that are still in beta, and drives make use of the page blob mechanism. Basically with a drive, what you can do is take an NTFS formatted VHD, those are the same ones that you can mount natively in Windows 7, and you can upload that into a page blob and blob storage, and you can use an API in a Windows Azure Compute instance to mount that drive. And you've then got a drive mounted as an NTFS drive that you can access using all of the managed or unmanaged I/O stacks that you'd use otherwise today. When you mount that drive, you either mount it in read-write mode, which means it can only be mounted to one instance at a time. Or you can take a snapshot and you can mount that snapshot as read-only. A thing to note with snapshots is if you do want to have a read-write snapshot, a snapshot is not a copy. Right? A snapshot is vector-based, so a snapshot only holds the difference between the underlying base blob and the snapshot. Think of it a bit like a differencing disk. Yeah? And again, we just use these like we would do a normal drive. Queues. Queues are a simple mechanism that we can use inside the Windows Azure platform for asynchronous work distribution. Create a queue. We create a message onto the queue. We basically do an in-queue operation onto the queue from one service, usually a web role. We then have a worker role that's polling that queue. It picks our message up with a dequeue message. It processes that work, and then it calls remove message. That gives us a pattern that ensures that every message is processed at least once. All right? It does mean that messages can be processed more than once. And the reason for that is if we do not call remove message within a sufficient period of time, which is configurable and defaults to 3 minutes, that message will reappear on the queue, which means it's potentially going to be executed more than once. It needs to be idempotent. Tables. Tables are effectively the NoSQL storage type in the Windows Azure platform. They are a key value store. Effectively, tables are typed property bags. Tables are scoped by an account. So within your storage account, you may have one person table. You may have one item table. You may have one product table. They are not strictly schematized. There is no enforced schema. Your person table could contain entities of dog, cat, person, sheep, banana, apple, orange, right, fruit. There's no strict schema there, and it's important that you remember that, right, because there are certain things that you want to do where you actually do want to take advantage of the fact that you can stick a variety of different data types into a table. They're designed for billions and billions and billions of rows. Right? The rule of thumb with Azure Table Storage or any of the Azure storage fundamentals is you should not be able to impact the performance of Azure storage. No matter how much load you place on it, you should not be able to impact the performance of Azure storage. If you ever think you've managed to impact the performance of Azure storage, please send me an email, because I'd love to find out how you're doing it, and it's something that I can talk to the team about. We scale out using partitions, and we're going to talk a lot about partitioning shortly. Partitioning is very important. Indeed, partitioning is the key to high-scale applications when it comes to data. Right? If you're not partitioning, your application is not going to scale. I promise you that. Because the only way it's going to scale is you're going to buy bigger and bigger and bigger database servers. Right? And big servers, ladies and gentlemen, have extreme diseconomies of scale. One 64-way Unix box, right, is a whole lot more expensive than 64 one-way Windows boxes. SQL Azure. SQL Azure is really, really, really simple. SQL Azure is SQL Server in the cloud. Nothing fancy, it's SQL Server in the cloud. You work with it like SQL Server, you attach to it with tools like SQL Server Management Studio. You can write stored procs, stored functions, create tables, indexes, views, the works. There are a few limitations. There's no CLR support yet, so no spatial type support. But for the most part, it is SQL Server in the cloud. Again, it is based on 3 replicas kept in sync throughout the data center. We can use all our existing client libraries, and we connect to each database directly. Right? That means that we aren't able to do things like use to jump between databases, and neither are we able to do anything like a distributed query or have our SQL Server database participate in a DTC controlled transaction. You buy one of 2 instance sizes with SQL Azure, either a 1 gig instance or a 10 gig instance. There is nothing in between. So it's either $10 a month or $100 a month. And they have a thing called the query throttle that limits the amount of resource you get to use out of the database. A word of warning, ladies and gentlemen, that query throttle is quite indeterministic at the moment. You don't know when it's going to kick in. Right? So it is a little bit hard to plan how many SQL Azure partitions you might need, right? Because you don't actually know what the performance of those partitions is necessarily going to be. And by non-deterministic, it is non-deterministic not only in that we don't know what it is at this point in time, but also that what it is at this point in time could be quite different to what it is next week. So just sort of a word of warning there when you plan out your applications. So that was our really quick 5-minute lap around these storage fundamentals. We're now going to talk about partitioning. Partitioning, guys, is really, really important. Right? Partitioning is the only way that you will build a high-scale application, right, with your data tier. Because by definition, storage ain't stateless, right? Everyone knows, we build these stateless web servers, right? And that way, to scale out, we just add more web servers and the thing just scales in a linear fashion. You can't do that with storage because we have a little thing that we call consistency that we need to maintain, right? You can't have stateless storage by definition. So we need to partition. And we usually have a couple of traditionally we've had a couple of reasons for partitioning because we've partitioned for a long time. We've partitioned with on-premise systems, right? And so the two typical reasons that you'd partition are that you've got too much data or that you've got too much workload. Right? We've got too much data for one machine, one database server. We've got too much workload for one machine, one database server. Too many bytes, too many TPC. Right? We also have a couple of new cloud-specific reasons that we might think about partitioning. Right? One of those is cost. In the cloud, we have differential cost across these storage types. Azure storage is significantly cheaper on a per gigabyte basis than SQL Azure. So there may be arbitrage to be had by partitioning our data across two different types of storage. And elasticity. The cloud brings us this offer of elasticity. And what I mean by elasticity is we can run along, selling tickets, monthly along most of the time, and then wham, bam, U2 goes on sale. That is elastic scale, ladies and gentlemen. We have hardware and capacity on tap in Microsoft's Azure data center that we can turn on when we need it. So we may choose to do a just-in-time partitioning strategy like we've done for Ticket Direct, right, where we normally have one database and we partition it to 50 databases for a period of time and then departition it again. Again, that's cost-driven to solve a performance problem. When we partition out our ticketing database, each of our partitions is less than 1 megabyte in size. Right? So this is not about buying sufficient capacity. This is about buying sufficient performance. So let's talk about some of the different types of partitioning. I'm sorry for the database geeks in the room. This may be a little bit like pulling teeth. We have this idea of horizontal partition. Horizontal partition is basically taking slices through your data. So here we're slicing our data based on what? Last name, right? First letter, last name. So horizontal partitioning is all about spreading our data across similar nodes. It allows us to achieve massive scale out in terms of both data and load. Right? If your application model is amenable to supporting horizontal partitioning, then you can achieve infinite scale. Right? You can achieve linear infinite scale. Right? Because we are dealing with partitions as independent entities. When we partition, intra-partitions are simple, right? Querying within a single partition is simple. Querying across partitions can be much harder, right? Find me all the people who are from contoso.com as a query. Is going to be a fairly intensive query because it's going to be a distributed query looking at every single one of those partitions. In terms of how I think that things work under the hood, again, I don't work for Microsoft. In Azure, here's how we go. So, Azure blobs, I would say, are horizontally partitioned by default. If you upload a really big file into Azure blob storage, there's a good chance that that blob is going to be split across multiple nodes in the data center. That is absolutely transparent to you. You are just dealing with a single named blob in a container. Azure Tables supports and encourages horizontal partitioning by default through the use of the partition key. You must provide a partition key for your data. So you are partitioning by default, even if you end up saying, I'm only going to have one partition, which I discourage you to do. Azure Queues, again, are going to be horizontally partitioned by default. The reason I can tell you that is they've stated that there's no limit on the length of an Azure queue. The only way you can give me a guarantee that there's no limit on the length of an Azure queue is you have to be doing something to be able to partition it, because otherwise, when I approach infinity, your server approaches fullness. Right? So you need to be chopping it up. SQL Azure. SQL Azure, you have to partition yourself. Right? So writing that partition logic, writing your data-dependent routing is something you need to do yourself. Vertical partitioning. So what's vertical partitioning about? Vertical partitioning is about taking slices down our data set. Right? So it's all about placing data onto dissimilar nodes. So what we might be doing here is placing frequently queried data into expensive, indexed, queryable, consistent, transactable storage, like SQL Azure, and placing large data, like 10 megabyte photo files, into cheap storage. Right? So we're basically optimizing for cost. Again, with Azure Blobs, I think it's unlikely that they're doing any vertical partitioning across nodes, but it could be that they will actually take one file and split it out across nodes. Azure Blobs are your ideal cheap storage. Right? That's where your big files should be going. Please don't let me find people putting binary data into SQL Azure. Only binary data that should be seen in SQL Azure is a timestamp column. Right? Otherwise, you're just peeing money away. Right? With Azure Tables, vertical partitioning is left to you. Right? If you want to vertically partition, there's not a lot of justification for doing that. You'd need to create multiple tables. Azure Queues, again, unlikely there's any vertical partitioning going on. Unlikely that we're taking queue messages and somehow splitting them out, but hey, we don't know what it's doing exactly under the hood. SQL Azure, vertical partitioning, left to you, but something that you should be thinking about. Right? Again, the example I had back here, this is all about, stick some data in SQL Azure, stick some data in Azure Storage. And we're going to have a bit of a worked example shortly. Hybrid partitioning is about gaining the benefits of both of these schemes, right? And you end up correspondingly with the limitations of both of those schemes. So hybrid partitioning is both vertically partitioning and horizontally partitioning at the same time. So what might we be doing there? So we may be saying, well, we'll actually horizontally partition our data into an array of SQL Azure databases, and then we'll vertically partition the data as well into some cheap Azure storage. To drill down in a bit more detail, if we think about horizontal partitioning, out of the box, Azure Tables support horizontal partitioning natively. So this means that when we create an entity, we provide that entity with a partition key and a row key. We can choose those keys arbitrarily, but between the two of them, they represent the unique way of identifying that entity across the entire scope of the table. So what we've got here is we've got partitions that we're going to drop in, right? And Windows Azure is going to automatically arrange these for us. Right? So we don't actually care too much about the relative sizes of our partitions. Because if you think about partitioning, right, normally what you're trying to do is to spread the load. Right? What you want to try and do in many cases is partition into sort of equal buckets. With Azure Table Storage, there is no need for your partition key to necessarily break your data into equal buckets. You should, however, partition as aggressively as possible. Right? So those partitions are auto-balanced for you. You don't need to partition into equal bins. With Azure Storage, hot partitions may be scaled up. And what I mean by that is if we see a lot of read-write loads suddenly starting to hit a particular partition, right? Remember, we've got 3 copies in the data center. Let me grab a Red Bull can. 3 copies in the data center. 1, 2, 3. Right? This one's been hit, been slammed. What we're going to do is we're going to find one of the other partitions. It's on a box somewhere. And we're either going to put it on a box on its own, or we're going to take all the rest of the load off its box, and then we're going to flip what becomes the master partition, right? So our master partition is now the one on the really high performance box. Red Bull high performance, right? Yeah? And so what's happening is transparently to the developer, underneath the hood, the Windows Azure fabric is moving your data around to optimize performance. Your partition key and row key make up your primary key, and you must include the partition key anytime you do a create, delete, or update. What that means is those operations, when you did them as a batch operation, can only occur within the scope of a partition. If you're inserting or updating multiple entities in a table, that can only happen within the scope of a partition. Select queries across partitions are parallelized and resource intensive. But, ladies and gentlemen, they are not necessarily more expensive. Right? Certain platforms charge you for what they call query compute time when you're querying their table stores, which is kind of this amorphous, who knows what on earth my bill's going to be like at the end of the month number. Windows Azure Storage charges you per query request. A cross-partition query is 1 query request. Just worth remembering that. It is more resource intensive on the server side. It doesn't necessarily cost you more money. A few things to note. If you make cross-partition queries, you are, at some point in time, going to end up with a continuation token back. A continuation token is the mechanism by which pagination is typically achieved with Azure table storage queries. So even if you're not asking for pages back, but you are querying cross-partition, you're potentially going to get these continuation tokens back. The reason for that, I hope, is fairly obvious. Because they are across multiple partitions, it is more efficient to give you some of the data back with a continuation token while the storage engine goes and looks for the rest of the data to hand back to you as additional pages. Your key columns can be up to 1K in size. That's partition key and row key. Be careful there. If you make them too big, you're going to end up exceeding the 260 character URI limit to be able to pull that data as a query out directly by that key. And what that means is you're going to have to use entity batch transactions in order to pull that data out via a query. Be aggressive. If you know you're only ever going to query something by ID, make that ID both the partition key and the row key. Have a partition of 1 entity. Right? That way the fabric can optimize heaps under the hood. Right? Be as aggressive as possible. You want as many small partitions as your application model can get away with, remembering that you are subject to having to include the partition key here and having a more resource-intensive, although not necessarily more expensive, query model. SQL Azure is different. SQL Azure is a whole lot more work for you. Partitioning is not automatic here. With SQL Azure, you need to create some sort of heuristic that you're going to use to route your data to an appropriate SQL Azure node. In this case, we're going to use the same heuristic we used last time. Right? So we're going to do an index of, and we're going to route to. Put the data on one of our 1 through 26 SQL Azure nodes. Who thinks that's a good idea? Who thinks that's a shit idea? Yeah? Why is it a bad idea, sir?
May not necessarily be evenly distributed.
Exactly, right? There are not many Zs, right? Anyone got Z as a first letter last name? Right? There's not a lot of Zs in many countries. Although in other countries, there's not a lot of A's and there's a lot of Z's. All right, go to China. All right? We haven't got a random distribution of data. All right? So when we partition for SQL Azure, we're partitioning for a couple of reasons. One, we're partitioning for data volume. You cannot have a database that's greater than 10 gig. The reason for that is underneath in the fabric that SQL Azure uses, they want to be able to move these data nodes around. Right? If you're sticking 10 terabyte databases in there, that's really, really hard. Right? It's hard to shift your data quickly enough to be able to dynamically adapt the fabric for performance reasons and for maintenance reasons. So you're going to be partitioning for data volume, and many times you're going to be partitioning for that transaction throttle. That's what we do in Ticket Direct, right? One database that's maybe under a gig to 50 databases, each of which is less than a meg, right? We are partitioning to beat the query throttle. All of that partition logic is left up to us as the developer. We have to come up with some sort of basis to distribute our data across those nodes, and that's typically going to be some sort of algorithmic mechanism or some sort of lookup-based mechanism. Those partitions are not auto-balanced. We are paying $10 a month for each one of our 1 gig databases. That means we need to try and use it to the full, which means we need to aim to have equal partitions. Equal partitions do not necessarily mean an equal amount of data in the partition. Right? Because equal with SQL Azure is a bit more than that. Right? It means not only the amount of data, it also means the amount of load that we're likely to be applying to that particular node. Right? So it's not as simple as it may seem initially. So, variety of ways that we can choose that partition key. We may have some natural partition keys. Countries, first letter, last name, date. Those are only going to be so-so, to be frank. I don't think any of those, unmodified, are an ideal partition key for using with SQL Azure. Potentially pretty good for Windows Azure, table storage. No good for SQL Azure, because again, I don't think you could ever make an argument that any of these are going to give you anything that approaches equal partitions. Right? If you do it by date, one end of the date spectrum is typically going to be busier and more loaded than the other. If you do it by first name, last name, we just saw that doesn't work. If you do it by country, well, we have big countries like your country, and we have little countries like my country, where we've got a population about half the size of New York City. Right? Not quite ideal. Or we can use some sort of mathematical algorithm, and we can use a mathematical algorithm potentially in combination with these natural keys. Finally, we may use some sort of lookup table. So we may actually build a lookup table that we use to specifically route certain portions and place that lookup table either in memory or on local disk or in some other high-performance storage location and read that out and use that to help us route our requests. So the modulo operator is a really useful operator that we can use to help with our partitioning. Modulo just gives us the remainder of a division. It has a really nice property for partition, and that property is that given two positive integers, m and n, m mod n will return a number between 0 and n. Right? So if we have data that is randomly distributed through the domain M, we can use modulo to give us 0 to n equally sized partitions. Kind of useful? Let's have a look at that. So I've got a little console app here that I'm going to run up, and I'll chuck this code up on my blog later today. So what I'm doing is I'm basically building 10 buckets of numbers, 10 buckets of ints. And I'm running through, I'm creating a GUID. So I'm using a GUID as my unique key. Right? And again, lots of people are going to use GUIDs as keys in storage. Right? The global unique identifier is a good choice for storage keys in these cloud-type environments. One of the nice things about a GUID, what is a GUID, ladies and gentlemen? Apart from a big, long string of characters. The hint is on the screen. A GWID is a 128-bit integer. Unfortunately, .NET 3, .NET 2 actually, does not natively support 128-bit integer math. So I had to use an external library to represent my big integer, and that gives me a massive performance hit that's going to disappear soon because .NET 4 does support natively 128-bit integers. So I'm going to run through here, and that's going to tell me that that's going into partition P, which is partition 5. So if we look here, it's basically taken my GWID keyed values and chopped it up into 10 equal partitions. Took a long time because we sat on a breakpoint. Right? Next, I've got a random distribution of data. Right? So a random distribution, this should work pretty well. Right? Again, we've got a random distribution. If we bin up that random distribution, we're going to get, once again, a set of broadly equal partitions. What if we bin a normal distribution? What are we going to get? What are our buckets going to look like? Like a bell curve of buckets, right? Exactly. We're going to get a bell curve of buckets. And it's pretty obvious. Right? There's our bell curve. It's kind of an inverse bell curve, but you get the idea. What if we take a list of the 1,000 most popular first names in the United States of America? Right? We get something that really is probably not an ideal partitioning mechanism. So let's jump back to the deck. So, in order to deal with situations where we do not have a random input domain, we need to use some sort of projection to project that into a random domain. To do that, we use a hash function. A hash function just projects one distribution to another distribution. Do not use a cryptographic hash function. Why don't we want to use a cryptographic hash function? Slow, right? Slow and expensive. Really slow. You want to use a hash table hash function, right? Hash table hash functions have a property of being really high performant and still producing a good random distribution. Plenty of choice on the web. Jump to tinyurl.com, whack part-hash for a good set of information. Be careful about using object.get hash code. You may be tempted to use object.get hash code. It works. You need to be careful when dealing with types that might be boxed or unboxed, because it can lead to some incorrect results there. So let's jump back into the code. So what we're going to do here is we're actually going to do a distribution, this time using the get hash code on our normal distribution. And so you'll see what we have there now is our data being binned in a roughly equal binned fashion. Again, we're dealing with small numbers here, so you expect a bit of variance. 99,000 to 10,000 and a bit is about right. With our real names, what we're going to do is we're going to use a hashing algorithm called murmur hash. Right? And we're going to use murmur hash to first hash the value of our data, and then we're going to apply the modulo operator to it. So we're basically taking our non-random distribution, turning it into a random distribution using a hash, and then we are using the modulo operator to bin that up into multiple buckets. And so again, a bit of variance there due to the fact that we're dealing with small numbers, but we are seeing a much more equal bucketing of our data than we saw previously. So I'll throw that code up on my blog later on. You need to consider partition stability over time. Repartitioning your data can be difficult and can be problematic. Right? So you need to come up with a plan for how you might do that. The first option is that you can literally do a complete repartition. So you want to go from 10 partitions to 100 partitions. You can go through and effectively copy all of your existing data, repartition it out across new partitions. Right? So you effectively spread it from being 10 wide to 100 wide. You effectively decrease the fill of your partitions. Think of it a bit like a B-tree index. Right? You're just respreading with a reduced fill. That will be a major pain in the neck if you have a large amount of data. The other is to use some sort of version partitioning scheme. So where as well as the partition identifier in your data, you also append a partition version number. And that way you can have something like that, where V1 may be partitioned into 4 buckets, and V2 may be partitioned into 10 buckets. That would give you a total of 14 bins. Just-in-time partitioning. So in SQL Azure, partitions cost money. They cost quite a bit of money. In highly elastic scenarios, you may not actually need your partition for much more than a few hours. If your load is predictable, and what I mean by if your load is predictable is you know when the load is going to start. You don't actually need to know where it's going to stop. You just need to know when it's going to start. If you have predictable load where you can predict the start of a peak in load, then you can just-in-time partition. You can literally say, we will add more capacity 2 hours before our known start time. We will then run at capacity until we sell all of our tickets, and we will then reduce our capacity at that point in time. And as I said, if you do this, it can be a hugely economical way of actually achieving something that is next to impossible in on-premise systems. Vertical partitioning. So vertical partitioning is all about balancing performance and cost. It's all about choosing to use the appropriate storage type for the type of data we're dealing with. Right? SQL Azure is fully indexable, transactional. You know, it's got all of those nice properties of a relational database that costs us $10 per gigabyte. Azure Storage has limited indexing. We pay a charge every time we query it. It's small, but we pay a charge every time we query it. And it costs us 15 cents a gig, or some 65 times less than SQL Azure. You are going to see some counterintuitive things shortly, right, that will make you sort of really scratch your head about exactly when you choose each of these. So, hybrid partition. Here's a quick exercise, sort of a thought experiment. Given that we've got this sort of data for a Facebook friends type of page, how would you do it? How would you do it? Have a quick think. So, here's how I'd do it. I'd do some hybrid partitioning, so I'd do vertical partitioning and horizontal partitioning. I would vertically partition my data into SQL Azure. As I got enough data, I would change that to be horizontally partitioned as well. I would duplicate that data in Azure Tables, right, along with my thumbnail data. So I'd have both thumbnails and the text data stored in Azure Tables, and the big photos would just go into Azure Blobs. All right? So put my searchable data into Azure Tables or SQL Azure or both. My thumbnails would live in Azure Tables. Any binary properties less than 64K, stick them in Azure Table Storage. Right? Because there's the potential to grab not only the binary data, but also associated data in a single batch query. So we want to use batch queries there to reduce our transaction costs. We're going to duplicate that data for each user. And what I mean by that is we are going to duplicate each of these users into every single one of their friends. So if Mr. Andrew Brust has 1,000 friends, Andrew Brust is going to be duplicated 1,000 times. All right? Put your full photos into Azure Blob Storage and potentially push those out using the CDN. So I did the math, and this is based on me actually running a model and saying, how much is this going to cost. So my math was 50 images per page, the thumbnail size of 3K, an average of 50 page views per month, and an average number of friends per user of 75. Right? And I did two models. I did one model where we had a proper normalized structure, right? So where we had friend and their friends, and we traversed the relationship, and then we retrieved all the blobs from each of their friends. All right? That cost 20.0026 cents per user per month. I then had one where I had it totally denormalized, right? So where I had a copy of each person in each friend's partition with the same numbers. I then had one transaction to get page N of data from that friend's table. So for me, go and get me my 50 friends in a single batch transaction, including their thumbnails. And then I insert the thumbnails in line into the page using data URIs. Data URIs allow us to encode into CSS, base64 encode images and send them down to the browser. By doing that, I'm saving myself some 52 transaction requests against Azure Storage. Those transaction requests at 1 cent per 10,000 actually add up. So by being clever with this approach, I can actually significantly cut my cost. That's some 30 to 40% reduction in the cost per user per month by massively duplicating my data and able to massively reduce the number of transactions I incur against the storage service. It may not look like lots when it's one user per month. It probably is when it's several hundred million users per month. Let's talk a bit about NoSQL non-relational data modeling, which sort of carries on from what we just talked about, and that we're talking about aggressive denormalization. So the thing with Azure Tables, it's not a relational database, right? Cross-partition queries are really resource intensive, and even if you're not paying more for them, they are going to take longer to execute. You're going to run the risk of getting back continuation tokens. They're going to be a pain to deal with. We want to aggressively denormalize, right? Because we want to reduce the number of times that you're going to be querying that store. So let's go through a bit of a worked example. So let's think about tweet storage, storing Twitter messages. Who uses Twitter? Few? Yeah, good. Right. So that's what a tweet looks like. It's got a tweet ID, a user ID, a date, time stamp, and a message. Really, really simple. So in a relational database, and we want to be able to search these messages. Find me a message that contains the word foo. In a relational DB, we might do something like that. Who thinks that's great? Who's a big fan of the like operator? Particularly with a percentage mark at both the start and end of the search term. Anyone? No one. Table scan time. Right, so we might say that's not really that wonderful. So we might do some denormalization. Right, so we'd denormalize to something like this. But we'd rapidly go, well, actually, as the length of our key kind of approaches the average length of our word, it's actually more efficient to do it like that. Right? So the thing with Azure Tables, we just go the whole way. Because storage is cheap. Real cheap. So what do we do here? Well, we actually say we're going to have a tweet table and we're going to have a tweet index table. And the tweet index table is going to have as its partition key word. Right? But it's also going to include the whole message. So if I want to find all the tweets containing the word foo, I just go and say, get me all the data out of the partition foo, and it gives me back everything I need, including the whole message. Because storage is cheap. Right? So that means I do one query instead of potentially one query to find the word to get some bloody set of IDs and then go and pull all those IDs out in separate transactions. Right? Real problematic. Yeah? So some interesting ways of approaching these sorts of problems, remembering that storage is cheap. Does that make sense to people? And of course, you can start getting really funky, right? So we might have a tweet, we might have a mention index, and the mention index has as its partition key user ID. So again, we also store the full message. So if I want all the messages for user CAULD, I just go and say, give me all the entities out of the partition CAULD. And I get all the data back, including the full message. Right? So I've now got 3 copies of every message, but storage is still really cheap. Right? So there are currently no secondary indexes, so we need to build our own indexes. When we build our own indexes, it's often sensible for us to actually store additional data alongside the index. Think of it as like being able to have a clustered index on every column. Right? If you're a SQL person, right? Like the performance of a clustered index on every single column. I'm going to jump over this. We talked about this a bit earlier. And I want to talk about architecting for better OpEx. So, when you move to the cloud, you are typically doing so for an economic reason. Technology is really nothing particularly new or fancy. It's just a different way of being able to pay for stuff. Right? And some of that gives us incremental improvement, and some of it gives us revolutionary improvement. The example of Ticket Direct, you just cannot achieve high performance for a 2-minute sales period to sell out a 200,000-seat stadium. You just can't achieve that in an on-premise system. Just can't be done. So it's important to understand the cost bases for your application. So storage costs us 15 cents per gig per month. These are all US dollar terms. The pricing is localized for about 18 markets around the world. You pay 1 cent for every 10,000 calls to the RESTful web services. Your storage charge is prorated. Right, so you only pay based on a period of time. So, for example, 100 gig for a day is going to cost you 50 cents. When you are creating blobs, you may be in a situation where you're putting blocks. An important thing to remember there is if you put blocks and don't turn them into a blob, they're going to stay on disk and they're going to cost you money. There's currently no way to delete a single block. So keep a track of what your blocks are. And if you have blocks that might be orphaned, put them into a blob and then delete that blob. Overhead can be expensive in tables. So if we have a table that has a Boolean value called onEmailList, the overhead of that is 2,200%. i.e. we're storing that massive string character in every entity in order to store 1 byte of data, which is the Boolean flag. Let me show you that in a bit more detail shortly. So 1 cent per 10,000 REST calls. That's that transaction charge I was telling you about. It may seem totally inconsequential, but it can have a major impact. So if you think of a queue, doing a queue will incur a minimum of 3 transactions. Enqueue, dequeue, delete. A page with 50 thumbnails in blob storage, where they're being retrieved directly out of blob storage, is going to require 50 transactions. You want to try and batch your transactions to reduce your costs. And therefore duplicate and denormalize your data to enable that batching. And there may be opportunities to pre-create data into blob storage. So for example, you could pre-create CSS sprites and stick them in blob storage. If you've got a page of 50 thumbnails, you could pre-create all of those 50 thumbnails into a CSS sprite tile. If you don't know what CSS sprites are, look it up in Bing. Go to bing.com, look up CSS sprites, magic stuff. All right? Pre-create your sprites, put them in blob storage, pull them down as a single request out of blob storage, and use CSS to chop them up into the individual thumbnails down on the client side. So have a quick look at a little calculator I wrote. I'm going to throw this up on my blog later this afternoon. It's just a spreadsheet that I use to hack around and do some modeling. I have a model of table storage. All right, and you might like to have a bit of a look at this. Basically, it shows you the sort of overhead you're adding by having a field like onEmailList. and how much overhead you could save by just changing it to E. Right? Now, as far as I'm aware, the team aren't doing any smarts under the hood to try and have lookup tables for these entity field names. Literally, each field name is stored in each entity. Again, it makes not a whole lot of difference when you've got 5 million entities. It does start to make a difference when you have 5 billion entities. Right? So just think about some of those sorts of things. Again, I'll make this spreadsheet available later this afternoon. SQL Azure, $10 a month for a 1 gig instance, $100 a month for a 10 gig instance. No one in the rest of the world actually has 1 cent pieces anymore. We all got rid of them. Nothing that drives me insane more than having pennies in my wallet over here. SQL Azure is prorated by time based on a day or part thereof where the day rolls over at midnight UTC. That's good for some people. It's not so good when you live at UTC plus 12 and want to do things in the middle of the night. So for Ticket Direct, we end up having to pay for 2 days at a time. Think of Azure, SQL Azure, like Windows Azure. Think of it as being an instance that has RAM, that has CPU, that has those sorts of resources. Because if you think of it as just bytes on disk as storage at 65 times the price of Azure storage, you'll freak out. Remember, it has no transaction charge. Session state. What's the cheapest way to do session state? Azure Table Storage or SQL Azure? Audience participation time. Who says Azure Table Storage? Who says SQL Azure? A few more. Who doesn't know? Who didn't put their hand up? Bloody good. Those were the 3 mutually exclusive possibilities. So, let me show you my session state pricing model calculator. Based on 5 million sessions a day of 8 minutes average length each, with a timeout of 20 minutes, 4 storage requests per transaction, based on using 200 1 gigabyte SQL Azure databases, that gives us a throughput of roughly 30 requests per second against our database. Here's the costs, ladies and gents. Using Azure Table Storage, $15,000 per month. Using SQL Azure, $2,000 per month. The amount we actually pay for storage is $1.45. We never really store any data for any particular length of time, right? The amount we pay for our transaction costs is $15,000 per month. As you can see, that transaction cost at 1 cent per 10,000 transactions can really add up, right? And it's not immediately intuitive as to which approach you should take. You should be modeling your application appropriately. I'll make this spreadsheet available. It also has a model for an application called Fluffy Photos. Fluffy Photos is a Microsoft sample application. I went through and did a static code analysis to model that, and I also modeled some of the storage transactions by listening with Fiddler. Talk briefly about building your own pricing models. You need to record all your assumptions, and if you have a look at my Fluffy Photos pricing model, you'll see those. Choose your scenario workloads. So effectively look at what are these workloads. Workloads are things like create a new account, upload a photo. They're not just page requests, right? Create a new account is actually 10 page requests. Determine what your workload requests per user per day look like. Then determine from that your resource usage. Storage in, transaction costs, data in, data out, and your static resource usage. How many bytes are you going to have on disk? How many SQL Azure instances do you need? Determine some application parameters. What can you tweak in your model? You can tweak things like how long do my worker roles sleep between requesting new data? I only allow images up to 800 kilobytes. Right? Calculate your required instances based on Generally, I work on a number of average requests per second. You may want some more sophisticated model that actually has a demand curve, and then just add instances, add resources to make those numbers reasonable. And you can then tweak your application parameters to really stress test that model. A few tips for Azure storage. Batch your requests, really important. You saw that transaction charge. That can actually sting you in the backside, so batch your requests. Model your usage, remembering that high-load, small storage scenarios may well be better solved by SQL Azure. Compress your blob data on disk. If you're going to serve blobs directly out of blob storage over HTTP, you can compress those and then set the content encoding header so they go out in a gzip encoding. Use caching to reduce your request count. Cache in your application tier, cache on the client side. And use CSS sprites and data URIs again to reduce that transaction count. Decide where your static resources live, right? Images that make up your UI. Do you put them in the web role where there's no cost to retrieve them, but they are consuming resources? Do you put them in blob storage, right? Where there's a storage cost that's basically nothing, but there's a transaction cost that could be quite a bit. Make use of CSS spriting, make use of data URIs. Those are going to reduce your transaction count. With SQL Azure, vertically partition large binary data columns out of SQL Azure. You should not have binary data in SQL Azure. Where you can, try and support dynamic partitioning. If you have predictable load, you should be able to partition dynamically. And pull your archive data out of the cloud onto cheaper on-premise SQL storage. So for example, with Ticket Direct, we pull events that have been sold and completed out into a data warehouse on-premise. So in summary, partitioning really is a key to working with data in cloud scale apps. We horizontally partition for scale out, really for performance and to be able to handle huge load and huge data volumes. We vertically partition to balance performance and cost. And you'll see that that can be quite important. It's important to choose appropriate partition keys, particularly when you think about partitioning in SQL Azure. And you need to think about modeling your applications. Build yourself a spreadsheet to model your applications. You're going to have a template up on my blog this afternoon that'll give you a good head start. And those pricing choices aren't always intuitive, right? When I first told some of the folks I work with at Microsoft about the differential in pricing between Azure Table Storage and SQL Azure for session state, there were a lot of scratched heads. It's completely non-intuitive. With that, I'd like to take some Q&A. It would be good if we could use them. It would be good if we could use the microphones. Otherwise, I'll repeat your question.
When you talked about denormalization, how does that work for updates? So you need to update.
Denormalization, how does it work for updates? So basically, denormalization and updates, what you do is you run some data grooming processes in the background. Right? So what you'll generally have is you'll have something that sits in the background and actually grooms your data. It's one of the justifications for what are called eventual consistency data stores, right? And that any type of data store that uses this key value, highly denormalized model, generally can't have full consistency because it generally involves massive denormalization and therefore needs a data grooming process. Other questions? Stunned silence. Sir in the front.
Is it possible to have like virtual hosts with one SQL Azure website? I mean, not SQL, just Azure web role.
Is it possible to have multiple virtual hosts? Yeah, so the question is it possible to have multiple virtual hosts within one Windows Azure web role? I think what you're trying to achieve there, sir, is you're saying, I want to run multiple websites within that role. The way I would achieve that is I would run a single Windows Azure web role, and then I would use host header mapping to split out exactly which site. So I'd basically build a multi-tenanted application. When the request came in, I would look at the host header of that request, and I would run the appropriate code for that request. If you want to get really fancy, you could say, right, well, we'll look at the host header, and then I'll go to blob storage. I'll dynamically load the .NET assemblies that I'm going to use to serve up that particular site. I'll spin up a new app domain, I'll hand that request to that app domain, process the request, tear down the app domain, and return the request to the browser. You may have some optimizations there to do where you don't tear the app domain down every time. What that would let you do is update the assemblies that are actually used for that particular site without having to tear down and redeploy the entire web ROM.
The reason I'm asking is we have multiple subdomains within our domain, and so we have to actually program that, right?
Multiple subdomains within your, well, it depends. I mean, what you'd do is you would, so the question is, we have multiple subdomains. You've got subdomains, basically CNAME all those subdomains to myapp.cloudapp.net. All right, and you should be good to go. And again, if you need to do something differently for each of those subdomains, just look at the host header and use MVC if you need to. I mean, you can use MVC to route to different things based on subdomain. Any others? No? Super. Hey, thank you all for coming along. Hopefully the slides will be up. There'll be a video up. Keep in touch on my blog. Email me, crystal@internet.co.nz. Follow me on Twitter, @CAULD. Been a pleasure having you all this morning. Please do fill out your evals. Comments on the back. I do read them, take them all to heart, pore over them jealously over the next few days, and cry into my tea leaves. So I do appreciate your feedback. Thank you all for coming along.